Hi, thank you everybody. Let me start this webinar talking about optimization and heuristics, how we can mix both optimization and heuristics to solve large scale or hard problems. And the idea is to get solutions quickly. So what's the summary? We are going to be talking about the first steps whenever you want to solve an MIP, then about control termination criteria for optimization, then how to seed the branch and bound process with greedy solutions in general or any type of solution that you want. Then I'm going to introduce two problems so that I can show with good examples how to use these techniques. Then I'm going to be talking about thinning out set of variables, then using divide and conquer strategies, and finally using LP as a guide within heuristics. So let's go to the first part. So for sure, the first step, and I have to stress this a lot, is to get a good model. And what do I mean about a good model? It's about getting a LP relaxation that should be close enough to the optimal MIP value. And bear in mind, it's not true that the smallest model will be the best model. In many cases, it's better to have kind of larger models with more constraints, as long as you get a tighter relaxation. And even in some cases, it makes sense to use cut callbacks. But well, we are not here to do that part. I'm going to assume that either you already did that, getting a very tight model, or you cannot really improve the tool that you have, and you have to do something with what the model is doing right now. So the easiest way to convert or to change the behavior of Gurobi solver is by determination criteria. And actually, this idea is used a lot in getting good solutions quickly. So in Python, well, you import everything from our Python interface, and then you can start, for example, changing the emphasis on the optimization run. So the two most important parameters to change the behavior of Gurobi will be the MIP focus, which essentially changes the way that the branching is done. I mean, we can either focus on getting good solutions or improving optimality or in improving the lower bound. And depending on the setting that you are, one of those will make a good choice. And also, if you're really interested in spending more time in heuristics, trying to get better or feasible solutions, then you can also control how much time during the branch and bound process Gurobi will use in heuristics, and that's done with the heuristic parameter. So, for example, setting it to a value of 0.5 indicates to Gurobi to try to spend about half the time in doing heuristics. You can also change the way you stop the optimization process by giving some quality guarantees. The two most common will be the MIP gap and the MIP absolute gap. So the first one is a range between 0 and 1, and it signals the solver to stop whenever it gets a proven gap. And it's important to remember that a proven gap between the current lower bound and the best solution of the given fraction. So the value goes from 0 to 1. So an 0.1 will mean to stop whenever you have a gap of 10% or less. You can also have the absolute gap, but there are other very interesting options too. So one of the things that controls the way the branch and bound exploring process goes is the cutoff value. So whenever you set the cutoff, you're telling Gurobi to don't explore any node whose value is, well, if you are in minimization, above the given threshold, and if you are in maximization, it's the other way around. But you have to use that with a lot of care. Actually, whenever you have a feasible solution, that solution induces a cutoff value. So if you don't have yet a solution and you set a cutoff value that is too low, you may be hurting yourself in getting the first solution. And actually, getting a first solution is very important. I'm going to talk about that in a bit more. There are another two parameters also very useful. One is called the best objective stop. and it tells Gurobi to stop whenever the best solution it has at hand is below the given value that you have. So regardless of the gap, if wherever you reach the given kind of hoped for solution, you can stop right away. And you can also do that with the bound, which is the next value. So those are ways of controlling the quality of the solution that you get. So you can use these criteria to stop your optimization early. And the resulting criteria will be an OR. So if you set more than one of these parameters, so the first criterion that is satisfied will trigger the optimization process to stop. But finally, you can also limit how much work you want to spend in a given optimization run. And there are at least these 4 parameters at hand. So one of them is set a solution limit. What does this mean? So this means the solution limit set to 5. It's telling Gurobi to stop whenever it finds a 5th solution, regardless of the quality. So again, if you set that number to, let's say, 1, it will stop whenever it finds the first solution right away, no matter what the quality of the solution is. So setting a low number will make it to stop very quickly, but again, the quality may not be as good. So if you want to play with it, a middle ground will it's more recommended. At least that's what I did in many of the things that I explore in some applications. There is also another very interesting parameter called node limit. So node limit is just saying to Gurobi, okay, you can do all that you want, but stop whenever you already process or explore this many nodes. So this is a way of ensuring that enough work is being done, but you don't want to really go all along to get a proven gap or something like that. You can also put limits in terms of the number of simplex iterations. And finally, you can always put a limit on the running time that you're willing to wait. The only disadvantage with running time is that it's really dependent on the computer that you're running, whereas the node limit or solution limit, you won't have problems with repetitions of runs. Those are the parameters to control how much work, what kind of quality, and what kind of emphasis you want to give to any given optimization. So what about given initial solutions? And I'm going to illustrate first how to do this, and then I'm going to explain when this helps. So here's a small piece of code, and actually this is the only complete code that I'm going to show you guys. Everything else is going to be in scripts that you're going to get whenever we release the video and the slides. And in this example, we are really just running from Gurobi and using NumPy to generate both the cost function and the weight function for a one constraint knapsack problem with, in this case, 50 variables. And the random values go from 1 to 100. And I'm going to set the capacity to have the sum of all the coefficients in the weight. So I build my model, I create an empty model first, then I add a set of variables. How many? As many as we defined before. All of them are going to be binary, and all of them have a name X something. We're going to set as a objective function the C vector, and we're going to maximize. And the constraint is going to be X times W, and that product should be less than or equal to B. So first, here we are setting that we only care for a gap of 1%. Whenever we reach that value or less, we're done. And now, with the problem already built, we're going to build a very dumb and simple initial solution, just to show you how to do that. So what I'm going to do, I'm going to keep track of how much capacity I've used so far, and I'm going to loop in all the variables that I define. So whenever the use capacity plus the capacity of the current element that I'm considering is below the total capacity, I'm going to set the attribute start to 1, meaning that I want to use that item in my knapsack. Otherwise, I'm just going to set it to 0. and then I'm going to call optimize. That's it. It's really setting those start attributes for every variable. And if you look at the log, you right away see that even before the optimization is performed, you get a message. Your starting solution was considered and has an objective value of 913.1 in this case. And actually, when you start doing the optimization, the first solution is that solution because none of the starting heuristics got anything better. But right away, in the root node, we already get, probably by rounding, just a very good solution with a gap of below 0.5%. So given that we set as a termination criteria gap of 1%, we are already done very quickly. So, okay, this is how you can, in any problem, load a starting solution. But, I mean, a natural question to have is when this really helps. When is going to help to have a starting solution? And there are several situations. One is when the initial solution is really hard to come by. And that can be because either the LP is very slow to solve or because the problem is just really big. And moreover, a quick solution is needed to do two things. First, as I said, it will help to prune the search tree because you won't go into nodes that have a value worse than the current incumbent solution. But that's not the only point that having an initial solution does. It also helps Gurobi to do kind of local improving heuristic on the given solution, or actually the current incumbent solution. So really having a certain solution can help a lot. So to show you an example of that behavior when this helps, I'm going to introduce two problems. One of them is the very well-known traveling salesman problem. That's the actually is the 1954 optimal solution to George Dancing TSP problem. And while the math, you all know it, I won't delay much. You have n cities, you have distances among every pair of city, and you want to visit them exactly once, and you want to have a tour, so a way to go from one to the other. And the objective is to minimize the total traveling cost. And the mathematical formulation is that every node has to have two edges turned on, and you don't want to have any subtour. So that's the TSP problem. And let me introduce a second problem, which is, well, a bit more complicated, but not too much. It's called the open pit mining problem. The idea is, as the image shows, you want to dig a pit. So the objective is every block, every little square that you see there has a valuation, and you want to maximize the NPV, the discount value over time of every block that you're extracting. And you are given some constraints. So you have some moving constraint or tracking constraint. You cannot move more than this many tons during the year because that's the capacity that you have with your trucks. And usually you also have a capacity in your processing plant. You cannot process more than this many tons every year. So what will be the description with some detail? So you have a set of blocks. For each one of them, you have a weight and you have a objective function, and you want and you have some time span where you're going to exploit this mine, and you have to decide if and when you're going to strike a block, and subject to those two capacities of tracking and processing. So the mathematical model, and again, this is not that important, but just to show it, you have these knapsack constraints on the capacities, you have the objective function here, and you have some precedences. So those are the capacities that I was talking, and these constraints down here are really saying, okay, if I want to get out a block, I cannot really get out the block if whatever is on top of it is not out already. And not only that, actually, you need kind of a given shape. You don't want the pit to collapse on itself. So that's captured by these precedents down here. Okay, so those are going to be my two problems. And let's go back to MIP start. How to do that? So for example, if you run our TSP example, this is a slight variation on our TSP example that comes with the distribution. And here you say how many nodes you want to have in your TSP, and the minus D is used to draw the final result. So as you can see, the solution doesn't take any time. It's very quick. But what starts to happen if you start to be more greedy? So in this example, now I'm asking for a TSP on 200 points. I want some verbose output, but I'm going to limit the running time to only 10 seconds. So if you do that and you see how Gurobi performs, you start to having a good or an LP solution very quickly, but it doesn't really find any feasible solution in 10 seconds, even though the problem is not that complicated, really. Something is really happening. So how we will build a starting solution for the TSP? And what you have to have is kind of a construction heuristic. In the case of the TSP, several heuristics are well known. One of them is called a greedy nearest neighbor heuristic. Essentially, the idea is to label every node as unvisited. And what you want to do is you're going to start from one of them. You're going to select the closest node. You're going to mark the starting node as visited. And now in the next node, you ask again for the same question. What is my closest node to the one that I have at hand? And you repeat the process, and eventually you'll visit every node, and that's it. So what happened now if I also enable, and this minus G is enabling in my script the greedy heuristic on the problem? So first of all, finding the first feasible solution is really trivial. It doesn't take any time, only, well, a fraction of a second. But now, two things really happen. So Gurobi accepts the solution, but actually it really improves right away. In just 1 or 2 seconds, it gets a solution of value 900 plus, and moreover, it actually proves that the solution is optimal very quickly. And here you get the drawing of the solution. So total running time over a little bit over 4 seconds. So that's very good. So essentially, you went from 10 seconds with nothing to 5 seconds with proven optimality. What about our open pit mining problem? So you can also think in this setting for a greedy heuristic. Remember, you have this patch of land, you have blocks, and you have, or you want to optimize the net present value of the mine. But you cannot take out the most valuable things. You have to take out things that are visible, so to say. So a very reasonable heuristic will be to, okay, let's look at everything that I can take out now because it doesn't have any precedence on top of it. And I'm going to choose the best one, meaning the one that has the best objective value. And I'm going to record how much capacity I'm using in my site constraints. And I'm going to update which blocks now can be extracted. So I repeat until I exhaust one of my capacities, and then I say, okay, I'm done with this time period, and I'm going to move to the next time period. So I reset my used capacities to 0, and I repeat the process with the blocks that I haven't yet looked at. So this is fairly simple. Again, if you think about it, it's really a greedy heuristic, just doing the best that I can with the options that I really have at hand right now. So now I'm calling my second script, this mining.python. The minus Z option is just given a size for the mine I'm going to be using. The minus T, again, is given a time limit, in this case, only 8 seconds, very tight. And I want some verbosity output. So if I don't do anything, actually Gurobi is able to find a very quick solution. It doesn't have enough time to solve the root LP, that's why the bound is so bad, but it does find a solution of value 41. And what they have here is kind of a summary of the solution. It says for every time period, what's the objective value that you get out in that time period, what the percentage of the total objective value you get here, and how much track capacity you use, and how much plant capacity you use, and how many blocks you get out. But if you look at the solution, it looks funny. So what Gurobi did was don't do anything from 0 to 5 and then start getting things out. That sounds a bit odd. And I'm going to get back into that. What if I enable my greedy solution? The heuristic that we were talking about, essentially getting out whatever I can, whenever I can, the best one. So first of all, the greedy solution gets a value right away of 245, way better than the 40 plus that we had before. And if you look at the solution, it kind of makes more sense. Be aware, I mean, the solution, the greedy solution is really the solution that we are looking at. We didn't give Gurobi enough time to even try to improve on this solution. So, and that's due to the very tight time limit that we set at the beginning. But I want to look into this greedy solution because here we see something kind of strange. The strange thing is that in the last 3 time periods, the overall objective that I get for the blocks that I get out into those periods is actually negative. So again, that's very strange. So let's go back to this. So the first thing is that Gurobi first internal solution, it's kind of weak. And we see that because it's waiting to the last time periods to start doing something. And it doesn't make sense because we know this is a net present value problem. So if you can do something later on, it will be better to do it early on. And also, the greedy solution that we built is using negative blocks at the very end. So shouldn't those two things be dealt by Gurobi itself? And well, yes and no. So Gurobi has things inside that help you cope with these two problems. One of them is preprocessing. Also, having a very good LP relaxation helps into dealing with these problems. But again, I mean, Gurobi, although we do a lot, it's not really magic. So remember, we are setting a time limit very, very small. 8 seconds is really nothing. And in this case, particularly in the mining problem, we do know something. We do know that in these problems, if you look at the blocks that are at the bottom of the mine, they're usually just filling in. They have negative objective, and also they are just using capacities. And so we know that those things probably you don't really want to use them. So that leads us to the idea of thinning out the set of variables. And actually, you can do that also in the TSP. And it's one of the key techniques whenever you want to solve very large TSPs. The idea that whenever you have very long edges, you probably won't use them in any optimal solution. So how would you do the thinning out of variables in the case of the TSP? Probably you will select a maximum distance and you will loop over all the variables. And whenever you have an objective that is too long, meaning that the distance is too long, you can fix the variable to 0 by setting the upper bound attribute to 0. And that's it, very simple. And actually, you can do better in the case of the TSP. If you use the LP to look into the reduced cost of the edges, you don't even have to guess what is a good distance. You use enough just to set an upper bound to 0 for those edges that have a reduced cost that is too large for a given value. And in the case of the open P, what you can do, as I said, whenever you have a block with a negative objective and it's just using up some capacities over time, you know, or you may guess that those variables won't be part of any optimal solution. So you can kind of fix those variables, or even better, not even modeling those variables right at the beginning. And actually, you can do a bit more, because you can count how much material there is above a given block, but by all these precedences, you can estimate a minimum time that it's needed to elapse for this variable to have a chance to be extracted. So that is also kind of limiting which periods a variable is available. So as I said, Gurobi does a lot of this, but it cannot really second guess all the structure that there is in a problem. So what happens if you use this idea in the mining problem? I'm going to show you first, if I don't do anything and I don't do optimization, again with a very tight time limit of 8 seconds, the problem ends up having 141,000 constraints and over 27,000 variables. But if you enable preprocessing, the situation improves quite a lot. You only end up having 46,000 constraints and only about 10,000 variables. So that's really, really an improvement. It's really around like a third. And whenever you can do that kind of thing, is really huge. And if you do that in the case of the TSP, for example, instead of having a number of square variables and the number of cities, you usually end up having like, I don't know, 10 times to 15 times the number of cities of variables. So that's a dramatic decrease in the size of the model you're solving. And that, of course, helps in the LP relaxation solving and in every node in the branch and bound tree. So what if now we mix this idea of having this pre-processing, using specific knowledge from the given problem that we have, and the greedy heuristic? So what I'm doing now, I'm calling, again, the same problem, same size, the same time limit, with pre-processing with the greedy solution and some verbose output. So again, the greedy solution is 248, but now since the problem is much more smaller, actually Gurobi is able to solve with the root relaxation, but not only solve it, it's also able to get a solution, a proven solution of 0.23%. So it improved the starting solution from 248 to this value of 262. It also, since we thinned out this set of variables, we were able to get a very good LP relaxation and actually prove that the bound is very good. And now, if you look at the solution, what happened? So we do get some value in the period time 8, but the problem decided that time period 9 and 10 are not really needed. You don't need to do anything on those. So that's really nice. So here you have an example where by giving a starting solution, you prune the search space, but also Gurobi is able to improve on that. And also by doing this preprocessing, the problem becomes simpler to solve and faster to solve. And that's really key. So, okay, that was seeding initial solutions for your problem at hand. But there is also a very common and widely used technique for getting good solutions quickly. And it's usually called local search. So why will make sense? Well, sure, problems get harder as they get bigger, but also they get way easier, much faster than you will think when you look at small pieces of your problem. And moreover, in many of these problems, it's natural to have pieces, natural pieces within the problem. So in the examples that we were talking about, in the case of the TSP, you can think that every segment, every continuous segment in your current solution is a sub piece to optimize. And we will see that this is quick to do. And also you can think on geometric zones of cities. So probably you can let everything fix it in your big problem, but you can focus on a geographical region. And let only to optimize within that region and get an improved solution. And in the case of the open pit, so a natural piece to have in that model will be time. I mean, you're working over time. So what you could do is, okay, you can fix a given solution for times 3 onwards, but I'm going to re-optimize the problem to see if I can improve only looking at what I'm doing right now in times 0, 1, and 2, or something like that. And how can you do that? How can you kind of let reuse the same problem to these kind of local search? What you need to do is have a subset of variables that you're going to let be free for the optimization, and you need a starting solution because you need the solution in the rest of the problem to have reasonable values. So what you will do is, okay, for everything that is not in your subset that you want to optimize, you're going to fix both upper and lower bound to the current solution or candidate solution that you have at hand. And then what you do is you optimize whatever is left of the problem, and you let Gurobi figure it out and simplify the problem and all that for you. So that's very easy to do. So let me show you what happens when you do this in the TSP example. So what I'm doing with the I flag of the script is enable the improving step. So the greedy solution gave us a solution of value 1035, but if you let the improving process, it finds in just a few seconds already improved quality solutions. So from 1035 to 1010. And if you do the same on the mining problem, so I have the greedy and also the improving heuristic enabled now. You see that the greedy heuristics start with a solution of 248, but by doing this optimization of time 0, 1, then 1, 2, then 2 and 3, and so on and so forth, fixing the everything else, you get very quickly actually improved solutions. So from the 248, you go up to 251, 52, 54, 55, 62, which is actually a very good solution. If you remember the bounce that we were getting before, this is actually the same problem. So that's very nice. I mean, you are actually, by using this idea of local search, even having a very big problem, you can focus on small pieces of your problem and re-optimize those pieces very quickly. But that's not all. I mean, you have to remember, in all these kind of local search heuristic methods, there is always a parameter, a natural parameter that will give a size of the neighborhood. So in the case of the TSP, for example, it will be the length of the segment that you want to re-optimize or the number of cities in a closed region that you want to re-optimize. And in the case of the open pit mining, how many consecutive time periods to re-optimize. So there is always this classical trade-off that you have to remember. The larger the neighborhood, the better the final solution I'm going to get. Why? Well, because actually I'm kind of optimizing larger pieces of the problem. So you are getting more global information into your local search strategy. But on the other hand, if I have smaller neighborhoods, I get faster optimization process. So I will go over more pieces of the problem quickly. And let me show you that in our two examples. In the TSP here, the script let me to say how big is the piece. So the minus S5 is saying, okay, I want to re-optimize my my current tour by looking at pieces of length 5 consecutive pieces. And well, you get some improvement fairly quickly. But if I now say, okay, but I rather work with size of length 10, well, as you see, you starting from the same solution, you do get to a better value. And the time, well, it's a bit longer, not too dramatically longer, from 8.3 to 8.5 seconds, but still longer. What about the open pit problem? Well, actually the same happens. Here, the minus S2 is controlling how many consecutive time periods I'm going to look at. So if I only look at 2, I get an improved solution from 558 to 583. And if instead of 2, I look at 4 time periods together, so I still start from the same greedy value, 558, but as you can see, I got a slightly better value. Not too much, but a bit better, 586. But the running time is fairly different. Now it's 30 seconds, and before it was only 22 seconds. So this is the larger problem, so that's why having a larger neighborhood, it's more costly. So you always have to remember that there is this trade-off, how big my sub-pieces are going to be and the quality of the solution that I am going to get. Okay, let's go to kind of a more interesting part for me, at least. And this is using LP as a guide in your heuristics. And this is a very powerful technique used in different applications. What's the idea? Sure, the complexity of solving MIP problems comes from the size, but mainly comes from the number of binary or integer variables that you have on it. So what we were doing in the local search strategy was fixing a whole lot of integer variables to given values and then optimize a piece of the variables that we want to or can look quickly enough. But an alternative idea can be to relax the integrality requirements for part of the problem and keep the integrality for a smaller piece of it. What's the hope? The hope is that the continuous relaxation conveys some information about the requirements, whatever they might be for your particular application, into the integer variables that you keep on your problem. So not doing just blind choices without looking at the future interactions, for example, or how the problem should behave in different pieces of a problem, but just trying to use the LP relaxation as a guide for that. So how would you do that in a code? Well, in the code, the only thing that you have to have is what are you going to relax? And for those variables that you are going to relax, you change the attribute from whatever you had, either binary or integer, to continuous. And that's it. So how can you do that? In the case of the TSP, again, one thing that you can do is, okay, I'm going to keep integrality for my time period 0, and I'm going to relax the continuous, the integrality requirements for everything else from T1 onwards, and keep the LP. And then what I could do is solve the LP with also the integer requirements for time 0. After I get the solution, I can fix those variables to the current value and then add back the integrality requirements for time period 1 and re-optimize and keep iterating until I reach the final time period. But you can do more. You can also do a fractional rounding based on the current LP that you have at hand. And actually, that's some of the things that Gurobi does internally, but Gurobi has to guess what are the important variables to round first. If you know more about your problem, probably I'm for sure you do, that process, it's way easier. And if you do that, then you can embed that heuristic as a node callback. So in some situations, that's very helpful. The idea of having this relaxing the integrality requirements for over time, it's a very well-known idea, as I said, and it's called rolling horizon heuristics. And the idea is, of course, very flexible. For example, you can keep integrity requirements for, let's say, 3 periods, but only fix the integer part for the first period and then move on onwards. You can also disregard some periods altogether. What I mean, okay, I'm going in, let's say, in the open pit mining problem, I'm going to keep the integrality variables in time 0. I'm going to keep the continuous variables in time 1, but everything else, I'm going to just forget about it. What I'm gaining there, I'm reducing the size of the problem by quite a lot. And what you could do to do that is essentially, as before, you set the bounds to 0. And actually, this idea of the rolling horizon risk can also be used as callbacks. A bit more expensive, but in many cases, this can be more effective as it's using more information in your problem. When is going to help? The idea of the rolling horizon or using these LP-based rounding heuristics for your problem. Here is really key to have a good LP relaxation. The tighter the relaxation, the better are going to be the results of guiding your solution. And actually, the open pit problem is one of those examples where the LP relaxation is usually very close to the IP optimal, within 1 or 2%. And in the case of the TSP, it can be, but the script that we have is not one of those examples. Why? Well, because although we are using subterranean inequalities, we are only using those subterranean inequalities as lazy constraints and not really as a cut callback. And why is that difference? Because lazy constraints are only bring to the front when you're deciding if an integer solution is interesting or not. So what you're losing by only using subterranean inequalities as lazy cats is all the P information that you could have. So that's a trade-off that you have to always remember. Lazy cats are nice, but if really you are using structural cats, it will be better to use them as a cat callback. So let me show you what happened in our open pit problem. So here I'm enabling the rolling horizon heuristic there. I also using the pre-processing part, and I'm enabling a lot of verbosity output. I'm not doing any optimization. I'm working with a way larger problem, size 20, and I'm limiting the size of my continuous part to only 1 period. And remember, the rolling horizon heuristics are actually construction heuristics. It's not improving over something. It's really starting from scratch to build an initial solution. And in this case, what you see is that it goes fairly quickly. So the first one is the harder one because it's larger LP model, and you get right away a solution of 277. And as you go along, you see that the time that you spend in the later time periods, it's faster and faster. Look here, I mean, just so that you can see that the problem is not trivial in size. This problem is 172,000 constraints and 54,000 variables after the pre-processing that we did. So some warning on the scripts that I'm going to share with you guys. They are going to be available for download whenever the webinar is ready. And they have a lot of options. So in the case of the TSP, you have how many cities, you can enable the greedy heuristic, you can enable the improving heuristic over the greedy, you can draw the final solution, some verbosity output control, the size of the sub MIP that you're going to use in the improving phase, whether or not to optimize, and setting a time limit for it. And for the mining, it's a bit more. You can also enable the use of callback heuristics. You have the greedy heuristic, you have the improving heuristic, and you can also decide to optimize or not to optimize. You can enable or not the preprocessing. You can try out the rolling horizon heuristic, which is already coded in there. The S, the parameter control the size of the sub-MIPs that you are using, both for the rolling horizon or the improving part. You can set, of course, a time limit, and this Z option controls the size of the problems that you're solving, and this will grow very quickly. And I have to confess, so my training in Python is fairly recent. I've enjoyed a lot, and I really see why so many people fall in love in Python, and I'm one of them too. But having said that, I know that the scripts have weak points, let me say. So please don't take them as a standard of doing things. It's just one way of doing them, and just as a guide. So thank you, everybody. I think we are ready now for the questions part.
Thank you, Daniel. This is Amal De Silva. That was a very interesting presentation. Thank you for that. So we have a lot of questions now. So we'll try to answer as many as we can. If not, we will answer them by email. So let's start with the first one. What is the difference between proving optimality and improving the lower bound? Is Gurobi still looking to tighten both ends when focus equals 2?
Okay, that's a very interesting question. When you're proving optimality, you have to second guess how much to spend both in improving the upper bound, meaning finding a feasible solution, and also improving the lower bound. So you have to balance the act. If you're only looking for improving the lower bound, then it's easy. You are essentially doing best node selection, and you are going to improve the feasible solution whenever you get lucky. So that will be the main difference between those two options.
Okay, so the next question is how much performance do you lose by doing all these heuristics in Python instead of like C or C++?
Okay, that's a very good question. So well, Python is a bit slower by nature, but it will depend on how much intensive computing you're doing in Python, really. Let's say just setting or fixing variables and looping into that kind of things, it shouldn't cost too much. Also, in Python, since everything can be done in more than one way, you have to remember that not all of them are as fast as it can be. And one such example is pandas data frames. So if you're looping into pandas data frames cells, that's going to be way slower than if you're looping in dictionaries. So you have to know some more things of the actual language. But the upside, I will say, on the Python is that it's really quick to do the prototyping. But yes, I mean, if the speed is the key, probably we'll go to either C, C++, .NET, maybe Java.
Okay, thanks. So the next question is, if I have a very large problem which finds a feasible solution pretty quickly, say less than 30 seconds, at the root node after a 60-second pre-solve, the solution is usually good or better than my initial guess. Is it worth putting in an initial solution for this problem, or should I just let Gurobi get it?
So if you are already getting a good solution, better than what you will get by your guess, right after pre-processing, then no, you don't need to add a starting solution, as it won't help. I mean, giving a starting solution will help when Gurobi either struggles to find a feasible solution, or the quality of the solution that Gurobi finds is not as good as it could be by just using your own heuristic.
Okay, thank you. So let's go to the next one. Can we load partial initial solutions to an MIP model? For example, if an MIP has 10 decision variables but I only have initial values for 7 of them, which I believe will be a good starting point for Gurobi to search the initial feasible solution? Can I load the initial 7 decision variables and
That's an
do that?
excellent question. Yes, I know what you're talking about, and yes, you can. And the way to do that is to set the start value to Gurobi undefined for the variables that you don't know the value, and just give the value that you want to try on those variables that you have a guess. So yes, Gurobi will be able to do that and try to guess. I mean, sometimes it will be successful and sometimes it won't, but yes, it will try to use partial starting solutions.
So the next question is, sometimes the solution converges well with heuristics heavily applied, but after some time it gets stuck at some MIP gap level with no visible improvement in time. A suggestion would be to use the feature of Gurobi to change the method at this MIP gap to searching for feasibility instead of this. Instead of doing this manually, is there a way for Gurobi to automatically change the method once the MIP gap convergence speed decreased?
Thank you for the question, and it's a good one, but unfortunately, no. Right now, the only way to do that is to do what you're doing. Essentially, stop it, change the MIP focus, and then keep going on.
Okay, the next one. When splitting up a problem by time, for example, an hourly model running for 1 month, split by day, is it best to make separate daily models or make one big month model and then march across days, optimizing each day and then the final entire run?
That's a good question. So it depends. So for example, if you are if you can do the search in parallel, then probably, well, you will have to have different copies of the model anyway. On the other hand, working on just one model and unfixing things can be easier and actually can be even faster because no matter what, Gurobi will always do pre-processing on the problem that you gave. You may not gain by having several different models in memory. So I would suggest just to work on one model unless you're doing parallel search.
Okay, thank you for that answer. And for the next question, if you're time constrained, I fully understand the value of the pre-optimization you're recommending. In my case, I'm not time constrained. I can leave 24 hours the optimization running and waiting to get the solution at the end. By your experience, should I implement a greedy approach, local search, etc.? My concern is not the time I will invest by implementing those, but the risk of possible good solution that I can leave out of the scope. Do you have a measure or estimation how far the optimum the solution goes when you implement the different tactics that you're showing us? Are some of these tactics free of risk of finding bad suboptimal solutions if I leave Gurobi running without time constraints? Did you get that question? Or
Yes, it's an interesting question. I don't have a good sense. I'm sure it will be dependent on the problem class that you're working on. So I've seen problems where doing this local optimization helps. When this happen more often is when the p-relaxation is bad. So if, like a general rule, in your case, the bound that you are getting or the final gap that you're getting after, let's say, 1 or 2 days, whenever you have to stop the optimization process, is still big, then doing local search will have a chance to get better feasible solutions at the end. Now, if after running whatever time you have at hand is already around 1% or below, I will say, no, why bother? I mean, keep using it as just a monolith call and you should be done.
I think this is a similar question to what you answered. How can a stopping criterion be set on speed of improvement, such as stop if the objective has not improved by more than a certain amount percentage in the past amount of time nodes?
That's a very good question. And internally, we don't have any way to do that in just one step. But what you can do is to control in every node the solution quality and the bound. So you can monitor in a node callback the progress, and if you decided that it's been too long without any improvement, you can tell Gurobi to stop the optimization process right away. So you can do that using node callbacks, and you can do that in all the interfaces. That will be the recommended way of doing it.
There are a few more questions. I think it's probably best answered via email. So we will send an email and reply to all the questions that we have not answered here. Thank you very much. I think we'll end the question and answer session now.
Yes, thank you, Drs. Espinoza and Da Silva. Really appreciate you presenting today and moderating the Q&A portion of this webinar. Thank you again for joining us. We hope you can join us for a future webinar and have a great rest of the day.